Greetings and welcome, friends, boys and girls, mathematicians of all ages. Today we're talking about measuring and constructing angles. Angles. So let's see. Here we go. Jump right in. This is from 1.5, by the way, in the Big Ideas Geometria textbook. I just like the in Geometria. It's so great. Let's see. An angle is a set of points. Okay, I like that. Set of points consisting of two different rays. Do we remember what rays are? Rays have an end point, and then they travel infinitely in a linear path, right, in a single direction. So two different rays. So here's one ray. Here's another ray right there. That have the same endpoint. So they both started at the same location, the vertex. Called the vertex. Have you guys seen the word vertex before? When we talked about polygons, this also will show up a little bit later as well in Algebra 2 terminology. It'll show up. Maybe, no, you might have even seen it if you'd covered quadratics, parabolas in Algebra 1. They had the vertex, right, was the point of change in direction, right, direction there. Let's see, the rays are the sides of the angle. Looks like I've got like a weird, when I copied and pasted, it got like a weird vertical bar there. That's fine. That's nothing. You can name an angle in several different ways. I love it. Here we go. So math is a language of symbols, so get ready. Use its vertex when you name it. So you could refer to as angle A. Now, challenge here is making sure your angle symbol does not look like a less than sign. Okay, so notice that the base of it is horizontal. So you'll have that challenge. It'll be okay. All right? Or like it's not a backward 7 or something like that either. Yeah. So angle, right? That's the symbol for angle. Angle A would be referring to the angle that has the vertex at A. In this particular sketch, that would be a sufficient way to name it. However, I want to point out that there are at least two angles here that have a vertex at A. There's this angle here, angle 1. Or you could have also thought of this angle that was on kind of like the outside, this little, Pac-Man right there. The bigger angle right there. So there are multiple angles there, but angle A is a perfectly good way to label this. Depending on the sketch, if there was more stuff going on, just referring to this as angle A would not be sufficient, because I'd be like, do you mean this version? Do you mean this version? Do you mean this version? So we do have to sometimes get more specific. Let's see, you could use a point on each ray and the vertex. So you could refer to angle BAC. This is more specific. This is like first, middle, last name right here. Or angle CAB. So when you read this, angle BAC, so imagine the angle that has B to A to C. All right, so that's the angle. That was the way I named it. Or C to A to B is how I named it. Now, I want to point out an incorrect way to refer to this angle. This is wrong. Would be to refer to angle ABC. That is not the same angle that they're talking about. Angle ABC would be referring to this angle that is not drawn. Okay? So the order of the letters matter. Basically, what matters is the middle slot. Okay? The middle slot is going to be your vertex. So when you name an angle, in this case, there's two ways if you're using kind of full name sort of arrangement. When you name your angle, the middle slot matters. Okay? It's all about that. And like, if you can get this right, you guys are going to be pretty good for most of this course. So let's see, you could also label it with a number, so I could call this angle 1. If I just have like a number written in the interior of that angle. Whoa, I just used another vocab word, friends. I just said interior. Here we go. Here's some more lingo coming your way. Some angle lingo. Let's see. Looks like the region that contains all the points between the sides of the angle is the interior of the angle, right? Interior. And the region that contains all the points outside of the angle is the exterior. Okay? That's nothing too crazy. I don't think so. I think it's pretty reasonable. Let's see. Let me So just vocabulary, naming angles. When we measured segments, we used distance. When we measure angles, it's going to be a little bit different once we get to that. You'll see in a moment. But here we're just still naming. Oh, okay, all right. All right, there we go. Feel free, internet friends, you can scrub through the video, skip forward a little bit, a few seconds. You might be able to avoid some of this awesome conversation right now. But who knows what mysteries you're missing out on, Mr. Waddy's secrets that I'm sharing right now. That'll be forever lost to time because you scrubbed right past it. How unfortunate. Angles. Angles. I was just thinking about the origins of the word angle. I actually don't know. I don't know if there's any Latin or English speakers that could analyze that word a little bit. I feel like I might have heard it before, but I can't remember. It might, no, anything I say right now would just be a guess. Might come from like astronomy, maybe like naval sailing stuff, who knows. Let's see, naming angles. A lighthouse keeper. Wow, guys, this story, I'm so into it. Measures the angles formed by the lighthouse at point M and 3 boats. Name 3 angles shown in the diagram. Guys, what's going to happen to the lighthouse keeper? This is amazing. Okay, so a couple angles. Let's see. If I wanted to refer to this angle right here, what's a name for that angle? Yeah, what do we got, Josh? JMK, right? And all of our angles, we suspect, will have M, the lighthouse, as their vertex and their middle letter. The same angle also could have been KMJ. Let's see, how about another angle? How about this angle right here? Yeah, Evan. KML. Yeah, no es más mal. KML. So angle KML. Pretty good. Does anyone know of another angle? Is there even another angle here? Oh, what do we got? Aiden, alphabetic Aiden. JML, the macro angle. Wow, I like it. And theoretically, I could also think of like angles this way, but that would be harder to describe. Yeah, I think we got all of them. And then there's, some variations on those where you could reflexive property, the angle name almost, and be able to get that like so. What else was I going to say? I feel like there was something I was thinking. Oh, this is what I was thinking. Because I mentioned the big angle. I bet you guys could come up with a conjecture regarding a relationship regarding the big angle and the little angles. And you could probably call it a postulate. We have a hypothesis here. Yeah, Jack? The big angle is the sum of the 2 smaller angles. That sounds like a pretty good conjecture right there. I bet we could even call it angle addition postulate in a little bit. But we're not there yet. Yeah. Let's see, before we get there, let's see, we had the ruler postulate for segment length. And here we've got the protractor postulate. Protractor postulate. Don't feel like you guys have to write this down. Postulate 1.3 is referred to in this text. That's not a standard name. No one else will know what you're talking about when you're doing math on the streets as you do. Which, by the way, math is not a crime. Unless, be careful. You shouldn't know supermassive prime numbers that are used for encryption of bank or government secrets. That might be a crime. Some numbers are illegal. So Don't think of those numbers. Stop trying to think about them right now. I know you're trying. Don't think about those supermassive prime numbers. You know the ones that we're not supposed to know. That is a prime. No, actually, one is not prime. That one always fools me. I feel like, come on, one, like, let's just give one honorable prime number. Can't we? Can't we? I don't know. So here we go. Consider the line OB and a point A on one side of OB. Okay, here we go. The rays of the form OA. Okay, all right. There's a weird. All right. Can be matched 1-to-1 with the real numbers of 0 to 180. Okay, so we'll refer to these as degrees, my friends. The measure of angle AOB, this is referring to the sketch, the image, the diagram, which can be written as M AOB. Okay, so this is M angle AOB, read as the measure of angle AOB, is not an image, it is a number. So this is a number, okay? Whereas this is the picture. If I was relating angles to each other, I could say that angle AOB is congruent to another angle. But if I'm talking about measures, I would say that measures can be equal, okay, to another angle's measure. So just like how we had congruent segments and equal segment lengths, similar idea at play here with equality and congruence going on. So let's see, the measure of angle AOB is equal to the absolute value of the difference between the real numbers matched with ray OA and ray OB on a protractor. So, all right. So notice, ray OB here is matched up with this 0. Just like how normally when we measure with a ruler, we start one of the points at 0. That's the typical way you would do it. And then ray OA here appears to pass through 140. So the measure of angle BOA is equal, because measure, it's a number, so I use an equal sign. Oh man, that equal sign's getting sloppy though. Nope, that's better. Is equal to 140 degrees. Now they also mention this whole absolute value of the difference thing. Let's say, actually let's just do it. I'm not even gonna say it, I'm gonna do it. Oh, let's see, can I open up my toolbar here? Ruler. Oh, watch this. Here we go, friends. I'm going to line this point up at O, and let's line this one up at, I don't know. Oh, wow, it's actually measuring angles up there. You guys see that? Oh, what? Look at those angles. This is an angle being measured with reference to the horizontal. Let's say I'm at, I don't know, looks like 60 degrees there. All right. Man, look at that straight line. Satisfactory. Let's call this point C. If I wanted to find the measure of angle, that's a terrible M, of, let's call it COA. That is not an O. Guys, wow. Here we go. That would equal this ray's measurement, 60 degrees, subtracted from this ray's measurement, 140 degrees, and absolute valued. Okay, so that what's that difference going to be? Looks like 80. Absval, which is 80 degrees. Okay? So it is possible to measure angles not having one of the rays or sides starting at 0, but in most cases it'd just be like, why would you do that? Right? Like why would, or the same thing with the ruler postulate. In most cases we'd measure starting with one of the endpoints at 0. It just makes good sense, people. Makes good sense. So that's how you can measure angles. Measure angles. Let's see, here's some language for classifying angles. You guys have seen these before. These are middle school concepts, I believe. So you don't have to, I don't know, just draw the sketch or something if you want, but I'm going to scroll past it pretty quick. So types of angles, depending on their measure, an acute angle is greater than 0 degrees and less than 90 degrees. a right angle. Oh, this is super important lingo right here. In our sketch, we measure a right angle, or we mark a right angle with a square box in that corner, suggesting that it is a square corner. Carpenters also have their tool called a square, or, you know, if you're an engineer and you're drafting on a drafting table, you have a square, which notice is not a square tool at all. Sometimes it's like a T or an L or something like that. Yeah, all sorts of, actually, they might have like a 30, 60, 90 triangle, but you'll use the corner to measure square, right? That's similar language there. But yeah, so you can mark a right angle with a box in the corner. So right angles, 90 degrees, bam, right, there we go. Obtuse angles are bigger than 90 and less than 180. So the 90-degree angle would have been here. So this one is beyond 90 degrees. And a straight angle is exactly 180 degrees. Well, we can refer to it as a straight angle, but you're right, we wouldn't often need to. It does come up in language for some of the angles we'll talk about tomorrow. But yeah, I mean, if you look at it, this is also just a line, right? These are two opposite rays that form a line. So yeah, it is a type of angle. I mean, and then I can also have angles that are more than 180 degrees. All right, those exist as well. Those would fit. I guess, yeah, I was just going to say we could say that's obtuse, but no, I would be incorrect. It would be obtuse not from this away, but from the other direction. Yeah. All right, okay, here we go. Keep moving, keep moving. Let's see, we ended up measuring already. I think I'm good. Let's talk about construction. Copying an angle. Copying an angle. So I'm just going to show you some of these images here, and we'll talk about how it works and why it makes sense. If I wanted to copy an angle using a compass and a straight edge, whoa, to construct an angle that has the same measure as another angle, in this construction, the center of an arc is the point where the compass point rests, and the radius of an arc is the distance, right? So here's the center of an arc, and the radius would be the distance to, you know, from one end to the other of the compass, like so. So here we go. If I wanted to copy angle A here and make a new angle that is congruent to it, you would first draw a ray, or a segment they did, I guess, yeah, because you're not going to spend forever drawing the rest of that ray, as shown, and label it as such. And then what you would do is you would set an arbitrary distance for that and draw that arc, and draw the same arc, the same radius on the original angle. And then what they did was they measured from intersection to intersection with their compass. So like, imagine if I could draw a cool compass here, it would look something like that. So you'd set that distance, so you have a new radius, and then you match it to your other intersection here that we already drew at point E, and swipe across, right? And now if I construct the ray that starts at the vertex and passes through the intersection of my arcs, I have constructed a congruent angle, which, by the way, congruent angles we can denote with little semicircle arcs. I guess, nope, semicircle is a full 180. Little arcs on the inside. You can have double arcs, you can have triple arcs, so everything that's got the double arc or triple arc is congruent to the other double and or triple arc things. Right, so there's a construction concept right there. Yeah, just so you know. Yeah. Let's see, two angles are congruent if they have the same measure. Let's look at this one. Here's an example. All sorts of stuff coming at you guys here. Yeah, wow. Look at quilting. Quilting mathematicians here. All right, it says identify the congruent angles labeled in the quilt design. So it looks like this angle and this angle are congruent because they have the single arc markers on them. So how could I refer to those angles? Because there's only one angle at this vertex, I could refer to that as just regular old angle G. I could have also referred to it as angle HGF or its reflexive version. And then what's a good name for this angle down here? Yeah, just plain old angle B is the easy way, right? So those two angles are congruent. Actually, I could even we might as well get accustomed to using our congruent notation there. So I could say that angle G is congruent to angle B, something like that, like so. And let's see, identify congruent angles. What's another pair of angles? Angle F and D. So I could say angle F is congruent to angle D, right? And that's how I would write that using that notation. Now it says the measure of angle ADC right here, is 140 degrees. What is the measure of EFG? Okay, so, yeah, you guys are quick. You guys are quick on this one. Now, what I want to point out, let's say if I have angle F is congruent to angle G, I can then conclude that angle, the measure of angle F is equal to the measure of angle G. The reason I can say that, which is probably obvious to you, is definition of congruent angles. Okay? Def of Kong is kind of the big idea. We use the same thing. There was definition of congruent sides as well. If the angles are congruent, then their measures are equal. It's really the big idea. And if the measures are equal, then I can substitute this into, wait a minute, I said angle G, guys. You gotta help me out here, friends. This was supposed to be D the whole time, wasn't it? Yeah, shame on me. Well, there we go, it's fixed. No one knows the difference. So let's see, so if this is 140 degrees, and I substitute into this, then the measure of angle F is also 140 degrees, right? Nothing too crazy, right? That just makes good sense. Good sense. Here we go. This was Jack's postulate, right here. Minute. The angle addition postulate, right? Which we just summarized as the measure of the big angle is equal to the sum of the measures of the non-overlapping little angles. That's it, right? Same concept when it was area addition postulate or segment addition postulate. Same idea, right? That if I want to get the big angles measure, I can just add up the little angles measures. Now notice angle measures, we are able to add angles. Like, I don't know if this makes sense. Angle A plus angle Q or something. These are pictures. Like, so adding pictures doesn't make as much sense. Addition works for numbers, but not really pictures. So you could apply it to the measures of angles, but you wouldn't necessarily, like, I don't think it would make sense to apply addition to angles themselves. Okay? And then there's just some, like, you know, geometry, algebra sort of stuff. Let me show us a last example of the day. Let's see. And so we've been measuring our angles, by the way, with degrees. Degrees are not the only way to measure an angle. I don't know if you realize that. There's also this concept called radians, which I guess, yeah, measures angles. Basically, it's all related to, like, the circumference of a circle. Degrees are an arbitrary measurement invented by mankind, related likely to the number of days it takes Earth to rotate around the sun, and the fact that 360 is a significantly factorable number. It's got the most factors of any number up to 360. So that's why, like, 360 degrees was probably picked for the number of degrees in a full circle. But here we go. So we're measuring in degrees, but I do want to point out that there are other measurements for angles out there. I think pre-calculus or trigonometry is when you'd see radians show up, which are an angle measurement that are native to mathematics. Okay, it's an angle measurement that just makes more sense in the world of math, although they're more awkward for us to be accustomed to. So let's see, it says this, given measure of angle LKN is 145 degrees. LKN, that's the big angle. Find the measure of LKM and the measure of MKN. Okay, so these two guys, right? Wah, wah, wah. So the big angle is 145 degrees. It's going to equal the sums of the little angles. So it'll be this guy plus that guy. And let's just substitute all in one go. So I'll have 2x plus 10, LKM, yep, plus 4x. Is that a minus or a plus now? Did I mess that up? It's minus. 4x minus 3. I could keep these in parentheses, but I think it's obvious they'll immediately be dropped. So if I want to solve this, wow, I was just teaching this to my Algebra 1 friends today. I could combine like terms, right? 2x and 4x and some other like terms here. It looks like 10 and negative 3. Those guys are friends. Hundo 45 is equal to 2x plus 4x. Yeah, you guys are algebra masters. 10 minus 3 is saving. Subtract 7 both sides. You guys are masters at this. See, 145 minus 7, 138 is equal to 6x. And divide by 6. Let's see, anyone know that off the top of their head? What was it? 23, thank you. So x is equal to 23. That is the answer to the x solution. But it is not the measure of those independent angles. So I would then find the measure of angle LKM. Also, that's starting to look like an L there. Would be 2 times 23 plus 10. And the measure of, we started with M on this one, MKN would be equal to 4 times 23 minus 3, like so. So I would then just plug those values in and fast forward. This is 56 degrees, and this one is 89 degrees. Now, as a check, I would expect these to do what? They should add to be 145. Looks like. Looks like. All right, so that was a bunch of stuff on angles. Thanks for watching, internet friends. Have a good day.